Hello all, I welcome you all to the fifth lecture in this course E690 ATM. So the last time we dealt with some abstract concepts about quantum mechanics. We discussed more in detail about the operators and the wave functions, and we kind of ended with a description of the Schrodinger equation. So today we will begin from the point of describing a Schrodinger equation and solutions to the Schrodinger equation. Okay, so let's the prime assumption is a particle can be described by a function. So psi of x such that the magnitude of psi of x square gives the probability to locate the particle at x. So this is something which is assumed. It cannot be rigorously defined. Okay, so let's assume that we have such a description of a function which gives you this information. Okay, so let's assume that we have a particle which behaves like this. Right, I am plotting as a function of x the mod x square. So what it means is the probability to find this particular particle at this point is the maximum, but there are chances to find it elsewhere at any other point. Okay, so what does this mean? There are two descriptions to this, or possible descriptions to this. The first one is, let's say if it's an electron which has a charge and the mass, can it be that the particle is distributed in the sense that, let's say you have something of charge E. Can E be distributed in this fashion such that integral E of x dx finally gives you the total E, the charge? Similarly, the mass can be written in this fashion. Is this true? Or the second thing to this is the particle is continuously moving such that the above plot describes its most probable positions. These are two different ways of looking at it, right? So the charge is distributed, so you can find it at this point, or it is continuously moving such that the probability to catch the point at the far edges close to infinity is almost zero. So it's almost circulating for a lot of time at the center, right? So this is, so most obviously based on our previous experience and such, you can always say that the second one seems more probable, but it has other issues, right? So let us say that this is a more simple wave function which can be explained by this, but there can be other complicated wave functions, not so complicated. Let us say you have a wave function which looks like this. Right? Which is not so uncommon. You must have seen this at many places, right? So there are certain regions in which the wave function comes to zero. Remember, the wave function can come to zero, but the very description of this is not both psi of x and psi dash of x both cannot come to zero. Right? If both comes to zero, then the only acceptable answer is the total psi is zero for the Schrodinger equation that we described previously. Let's not get into there, but let's say only this example where you have the wave functions come to zero here. So if the wave function come to zero here, so there must be some potential which is high enough for the wave function to drop here, right? So you must have some infinitely high barrier here wherever the wave function comes to zero, right? You should have an infinitely high potential such that the wave function came to zero at this point. So if we talk about this solution or this idea that you have a particle which is moving around, but the probability of finding the particle in these places is what the wave function actually tells you. Again, we land up at a problem, right? So we have infinitely big potentials. Let's just say that your particle somehow reaches to this point, which also has a probability to be present, right? The particle, the red particle, can somehow be here for some time, and it has to move from here to here, right, to achieve this particular distribution, and it has to move from here to here to achieve this particular distribution. So if you have infinitely high potential walls, how did the particle get past this? So the correct answer, or the correct thought according to the current understanding, is that we cannot describe a particle to follow a linear path or a 3D path where we cannot trace the path of the particle. We can only tell that it just disappears here and appears in the other place, irrespective of what path it takes. We don't know currently. It is not possible to know what path it took to go from one path to the other, right? So this is kind of weird, but this is what the wave function actually tells you, that you don't know how it went from one place to the other, but the chance of finding it here at any point can be identified by the magnitude square, right? So let's proceed from here on. Let's take it for granted that this is true and proceed from here on, right? So in this regard, we saw that the wave function psi at any time x and time t can be expressed by this continuous description. If we have wave functions are continuous and we have functions which are continuous, so we have e power I kx minus omega t dk. So we saw that you can have infinite, so basically e power I kx minus omega t, they are the basis vectors for the continuous function, infinite dimensional space, and any function in that infinite dimensional space can be expressed as linear summation of such infinitely long set of functions, and such infinitely long set of functions can be integrated, right? So this is the reasoning behind this, and this definition is very similar to the Fourier transform that you have previously seen, right? So this is how all these things came into picture. Now if this is true, right, if I assume that this is the wave function, then I take this operator I h bar dou by dou t of psi of x comma t. If I do this, and of course this 1 by root 2 pi comes because of the normalization conditions, right? We assume that the wave function, the particle exists somewhere in space, and 1 by root 2 pi comes from there on. I get 1 by root 2 pi integral minus infinity to plus infinity psi of k. I assume psi of k is time independent, which may not be always true, but I'm just taking here for an approximation, okay? Dou by dou t e power I kx minus omega t dk, and this obviously will give out 1 by root 2 pi minus infinity to infinity psi k, and I h bar, okay, so I forgot an I h bar here, which will give you h cross omega e power and we know from our previous experiences h cross omega is an unit of time, sorry, it's a unit of energy, right? It's E. So I h cross dou by dou t is an operator, so this is basically E times psi, right? So so energy is an eigenvalue of the operator, energy E. I call this some constant E, okay? For now we will at the end of our lecture we will see that h cross omega is indeed energy. We will prove h cross omega is indeed energy, but let me point out that now I just use E as a variable, right, and call it energy here now, but obviously I will prove this later on, okay? This energy E is an eigenvalue of an operator we call this an energy operator, but dou by dou t, right? So this is what we see here. Obviously, if E is the energy, right, and we previously saw what is the total energy of a system. That is described by the Hamiltonian, right? And which contains two parts, T being the kinetic part and V being the potential part. And the kinetic part can be written by, right? And if you're talking about one-dimensional systems, V being the potential, we can write as V of x. And Hamiltonian is written in such a fashion that the kinetic energy is a function of only the momentum and the potential energy is a function of only x. This is the common way of writing the Hamiltonian, right? So if this is true, we come up by this. And now, because this also gives, so h psi acting on the wave function should also give you an energy operator, right? H being Hermitian, because we take it that the kinetic, we prove P is Hermitian, P square is also Hermitian. And if we take V, which is also a Hermitian operator, if it appears to be a Hermitian operator, right, then H psi will give you E psi. Then E will be real. E is the energy. And we saw this E. Okay, sorry. You should not have a cap here. It is just, it's not an operator. Is E hat psi, which is IH bar dou by dou t. So we get back our original Schrodinger's equation, so which will turn out to be IH cross dou by dou t of psi, which is minus h bar square by 2m dou square by dou x square psi plus v psi, right? So this Schrodinger's equation has some properties. It has only the first order differential in time and the second order differential in space, and both of them are linear, right? Differential operator is linear, first order and second order and as well. So if psi 1 is a solution to the Schrodinger's equation and psi 2 another solution, it is true that psi, which is a linear combination, is also a solution. So this is the linearity of the equation. Because it's a linear equation, you can clearly see if I substitute psi 1 and psi 2 and also psi, you can clearly see the capital psi is also a solution, right? And the second point is, if V, that is the potential energy, is time invariant, in the sense when we write this Hamiltonian H, P square by 2m plus V, if this V is just a function of position and not of time, right, then we can split this psi of x comma t as two components, psi x into psi t, such that psi x is a function of only x and psi t is a function of only time, right? Why is this true? Because if, let us say that x and t are intermixed, then if we say that the potential has x and t as intermixed, then when it acts on psi, then you will have cross components, right? Because this potential, the momentum we know to be a function of only position, that because the kinetic energy is a function of only position, right? So that is already known. Then now let me substitute IH bar dou psi by dou t can now be written as IH bar psi x d psi by dt, right? Because psi t, because I have split it into two and psi t is a pure function of t, so the partial differential is now converted into normal differential, right? And the second part, minus h square by 2m dou square psi by dou x square gets converted to minus h bar square by 2m psi t d square psi x by dx square. Again following the previous thing. Now I h bar psi x d psi of t by dt will be minus h bar square by 2m psi t d square psi x by dx square plus v of x psi. So this is psi x psi t, right? Because yeah. Now if I divide throughout by psi x psi t, then I get I h bar 1 by psi t h bar square by 2m 1 by psi x d square psi x by dx square plus v of x. You can clearly see this part is a time dependent and this part is time independent. Right? And this equation where you have two sides to be very different, right? This one does not depend on space, this one does not, the right one does not depend on time, and the left one does not depend on space. And this can only be true if each of them becomes equal to c, some constant. Okay, so again for our purposes, I'm going to call it E, the energy, right? So I h bar 1 by psi t d psi t by dt is E, the energy, and on the right hand side minus h bar square by 2m d square psi x by dx square plus v of x psi x is equal to E psi of x. Remember, this form is the same form in which we got this derivation, right? We got E psi here, we got E on the other side as well, and hence that's how we started with the Schrodinger equation derivation, right? So it's the same thing, it's just written differently. I just split the spatial and the time component, and again we get back to the same form. Now this one is very easy to solve, that is the time component is very easy to solve. So the solution to this is d psi t by dt is minus E I by h bar psi t, and you know that psi t can be of the form e power minus IE by h bar into t, right? And if psi x is the solution on the right hand side, I don't know yet. Okay, so the total solution psi will always turn out to be psi x, the spatial component or the time independent component, into e power minus IE by h bar into t. So this is the most common way of writing the solution. If the potential is time independent, we use what is called as the time independent Schrodinger equation, which is h cross psi x is equal to E psi x, E being a constant, right? And the solution total psi can be written as solution from this time independent function into e power minus IE by h cross t. Okay, and once again it's easy to see that this is an eigen equation, and there can be many solutions. Such that psi 1 so on till psi n with energies E1 so on till En. This is very similar to how we saw the solutions of the momentum operator, right? In our previous class, we defined P as h bar by I dou by dou x, and we know that if this is true, then the solutions are plane wave based solutions, and you have each solution as an independent energy and such, right? This is the same fashion. And the total solution psi, let me write it capital if I can remember it everywhere, can be written as some summation 1 to infinity Cn psi n e power minus IE by h bar into t. Right? So this is the time component, and this is the independent solutions, and the total solution is some average, and the Cn is the Fourier components, right, or the component of each stationary solutions. And you can obviously find Cn by if you know the starting point, because this is how we started this derivation, right? If you remember from our previous class, we begin this description by saying that if we know how the wave function looked at time t equal to 0, because let's say we know psi of x comma 0, how it looked, right? And we wanted to know, given a potential v, how it transformed, right? So how do we find Cn? Because now we have found out a general solution. Cn can be obtained by the inner product. With any psi n. We will do some examples and then we will clearly understand what we mean by this, right? So for any given problem, we can imagine an initial solution, and at any time t we can find the solution by calculating its Fourier components. Okay, so there are, once again, if we have this kind of a solution, there are few things that we have to understand. The first one is the solutions psi 1 so on till psi n, the eigen functions of the Hamiltonian, are stationary states. What we mean by stationary states is that their the magnitude, let's say, of n square does not vary with time. It's easy to see because here psi n of x comma t is assumed to be psi x e power minus IE by h bar t, right? And how do we find the modulus psi n square? Is psi n star psi n, which will turn out to be, let me some integral e power minus IE by h bar t psi n star e power minus IE by h bar t psi n dx, right? So the time component gets vanished. So eventually you will get the same solution when the time component is missing, right? So basically you will get psi n of x square. So the actual wave function does not change, as well as the expectation value does not change, is time independent. Okay. However, the total wave function the solution, which is a linear summation, capital psi n, psi of x, which is a summation of psi n's, is time dependent. What we mean is, this guy is stationary, is time independent, right? But then this random summation of such wave functions which are which are stationary will turn out to be time independent, because the summation of e power minus I e by h bar t will not all cancel out. We will see examples of this, that the solutions are the eigenfunctions of the Hamiltonian, h psi n equal to e psi n, right? So the psi n's are eigenfunctions of the Hamiltonian. These eigenfunctions are stationary, but the actual solutions, which are linear summation of such stationary eigenfunctions, need not be time independent. Okay, so let's go and look at some examples, and then we will understand these derivations. We'll understand these statements more clear. So let's go to our first example. One is particle in an infinite square well. So let's assume this situation. We have a particle which lives in this world where we have this infinite potentials. So I draw it like this because let's assume this extends to infinity. This is at x is equal to 0, this x is equal to a, right? So this infinite potential, in the sense we can think of this place as at T extremely high, right? Some 10,000 Kelvin or something like that. Here also temperature extremely high, or potential electrostatic field being extremely high, the repulsion being extremely high, right? So you are at that point. Let's say you have a really dense electric field, but in contrast to how practical potentials are, there is a steep wall here which dies down. So the potential dies down very steeply. Conventional, let's say, temperature potential or electrostatic potential does not die off like this, but this is an instructive example. Okay, so the potential V equal to infinity here, and here V equal to 0 from 0 to a, right? So now we have, let's say, two different kind of regions. The best way to solve this is to solve this in two different regions. So I'm going to call this regime 1, I'm going to call this regime 2, and the definition of the problem is V of x equal to 0 for 0 lesser than equal to x less than equal to a, and infinity otherwise. Right? So now let's say in the region 1, let's solve the time independent, because the potential is time independent. Obviously you can now split the wave function in time dependent, time independent form. Now in region 1 you have minus h bar square by 2m d square psi by dx square is e psi, right? Because V is 0, so in region 1 the potential energy is 0, the kinetic energy only exists. So the solution for this is pretty straightforward. You must have seen this in many places. So this is psi d square psi by dx square is minus k square psi, and k is 2m e by h bar. You have the wave vector here because the solutions of this can be written in two forms. One is the exponential form, the common e power minus ikx form, or here I write it in this particular form. Both are equivalent, but I do this because we will plot these functions soon enough so that it's easier to plot the sine and cosines other than the exponentials where you have two summations, right? So let's see. Okay, so what are the boundary conditions? Obviously the thing to do is, so we have solved the problem. Now On the other region, it's actually pretty straightforward before going to the boundary conditions. In region 2, when potential V tends to infinity, right? So the way we can write this is minus h bar square by 2m d square by dx square into some psi plus v psi equal to e psi, right? If v tends to infinity, the only way this will have a non-trivial solution is when psi tends to 0. So the only trivial solution is the only solution that you can have, right? So we assume in regions where the potential tends to infinity, the wave function dies down to 0, right? So in the second region, the wave function dies to 0. So the solutions are, you should have the solutions which match at the region boundaries at x is equal to 0 and x is equal to a, the psi should match. And when we do this, you can clearly see that b will tend to 0, and let's say a sine kx tends to 0. There are two possible solutions to this, a tending to 0 in the sense the wave function is completely 0, and the other non-trivial solution comes when you have kx equal to n pi, and sorry, ka equal to n pi, and k is n pi by a, and n goes from 1, 2, 3, so on, right? So the solutions, that is psi of x, can be plotted across x. This is 0, and let's say this is a. For n equal to 1 will turn out to be something like this. For n equal to 2 will have a node, and for n equal to 3 will have 2 nodes. Right. These are 3 solutions, and let's go back and look at our constraints for the okay, so before we go any further, so the solutions are a sine pi x by a, and this is a sine 2 pi x by a, and this is a sine 3 pi x by a, right? So given that these 3, of course, see, these 3 are just eigenfunctions, right? So these are eigenfunctions of the Hamiltonian, and these are still not the actual wave functions of the particle, right? They are just solutions to the Schrodinger equation, and then they are just the eigenfunctions. The particle is the Fourier summation of all these things, right? But let this first property of this is these psi-n's are orthonormal. Right? How do we find this? Integral, let's say psi I star psi j is del ij, right? You can integral minus infinity to infinity. Let's take an example. A square sine 2 pi x by a sine pi x by a. You can clearly see that it will turn out to be 0. I encourage you to try this, right? The second is psi I square is time independent, right? Why? It has only the x component, and psi I of x comma t is just, let's say, the first one. Let's say psi 1 of x comma t is a sine pi x by a into e power minus I e. What is the first energy? Is just pi by a. Okay, we'll just, let's say, e1 by h bar t, right? And psi I square is integral minus infinity to infinity a square sine square pi x by a e power minus and plus is constant. So this is again time independent. Now how do we find a? The right way to find a is, instead of doing this for just one, we can do it for all of them. So psi I square should be equal to 1. So integral minus infinity to infinity a square sine square kx dx equal to 1. Of course, it is only defined from 0 to a, right? Because it's anyway 0 beyond minus beyond a and beyond 0 on the left hand side, right? So it is only 0 to a. And if this is true, it's easy to see a square will turn out to be 2 by a, and a is root 2 by a, right? And the third, the energy E is h bar square k square by 2m, and k is n pi by a. So E is n square pi square h bar square by 2ma. So E does not depend upon the particle energy, does not depend on A, and A is the amplitude. So A is this, right? And why? In classically, the energy typically depends upon the amplitude, right? Whereas here it depends on the K and not on the amplitude. So this is a big departure from classical case. A wave energy depends on the square of the amplitude, but here the wave energy does not depend on the amplitude but depends strongly on the frequency. You already get to have a feel for why a wave is very different from a particle, right? So this is something very important. This we got from a very trivial case of an infinite potential wall, right? So this is the observation from an infinite potential wall. Now let's go to another very important example, that is the example of a free particle, which will seem all the more easier than what we considered before, but gives us some very fundamental insights into how the quantum mechanics works and how it is different from the classical behavior. Okay, so in a free particle we assume that the potential V of x is 0 everywhere. Okay, so let's write the Schrodinger equation: minus h bar square by 2m d square psi by dx square equal to E psi. And the solutions for this is from the previous case, but now we will not use the sines and cosines, but let's use the exponentials. Okay, psi is a e power ikx plus b e power minus ikx. We're not going to draw the wave functions anymore, so I'm just sticking back to the exponential function, which is easier to write. K is root 2m e by h bar, very similar to what we had previously, right? And you can write psi as a function of x comma t in this fashion, minus ikx, right, minus h bar k square by 2mt, right, because minus ie by h bar t, and e is from here, e is h bar square k square by 2m, right? So I just substituted that here, plus b e power minus I kx minus h bar k square by 2mt, right? Just I'm making it as a time dependent by multiplying the psi t component from our previous derivations. Now you can see that because this is a free particle, k can take any values. So k is continuous. Similarly, the energy E is continuous. This is in contrast to our previous example where we had infinite potentials, where k and E were finite, right? So here k and E are continuous for a free particle, right? So here let us take one of this. Okay, let's take the first component. So I'm just going to write psi a here, which is a e power minus I kx minus h bar k square by 2mt, and d psi a by dx will give us ik psi a and d psi a by dou t will give us I h bar k square by 2m into psi, and dividing one by the other you get dou x by dou t, which is the classical velocity, which will turn out to be h bar k by 2m, right? And if I substitute k by energy, you will get E by 2m. So this is the velocity of this term, right, the first term, and the second term's velocity will turn out to be minus h bar k by 2m, and obviously the magnitude is just E by 2m. So what it means is the term with a positive k feels as if it is going with a positive velocity in the x direction, and the term with the minus k seems like it is going with a negative velocity. So the two terms k and plus minus k seems like you have two waves which is moving in the positive x direction with a particular velocity and moving in the negative direction with a negative velocity, right? So this is the description of the wave, and it is its apparent nature, right? But if v is the classical velocity, and if let's say if the kinetic energy is half mv square, you can see that the classical velocity will turn out to be root 2e by m, which is twice the quantum velocity. Let me write this as v cube, right? So what makes the free particle, which is moving with without any potential, having a velocity in the quantum picture having twice smaller than what we see in the classical case? So v classical is 2v quantum. So this is an apparent contradiction. With classical physics, which is a problem, right? So because velocity is an observable, previously we had other things which are not observables, which are contradictions. that's fine, but you cannot have a contradiction in the observable because the classical physics have been proven to be true uh, time and again. So you cannot have such a contradiction. So we have to actually explain why the velocity of a free particle, that is the plane waves that we have considered here, is twice smaller than the classical particle. The problem is size that we have considered here, right? Psi a, psi b, and the summation, something like e power a e power kx minus h bar k square by 2mt is not normalizable, right? So let's take this. What's the magnitude of psi a? Which will turn out to be minus infinity to infinity dx, which is actually infinity. So psi a is not square integratable. Therefore, the free particle plane wave size psi a and psi b do not belong in Hilbert space. Right? So what's the problem? Where did we go wrong? The mistake is again very simple, right? So the size psi a and psi b are solutions to the eigen equation, and they are just eigen functions or vectors. The actual wave function of the particle is psi is basically 1 by root 2 pi integral minus infinity to infinity psi k dk. Right. So the actual wave function is a Fourier summation or a Fourier integral of the eigen functions, and it is this which is a particle, right? So it is something which is localized in space, and hence this summation can be proved to be normalizable, whereas the eigen vectors, that is the plane waves, are just not normalizable. And how do we find psi k's? This is pretty straightforward, right? So this is psi k psi of x comma 0 at time t equal to 0. If we know psi of time t equal to 0, if you know the wave function at time t equal to 0, we can find psi k, that is the coefficients, by doing this, or writing in this integral form. Infinity can be written as psi of x comma 0 e power minus I kx dx. Remember, these are minus, right? So basically, depending upon size, so let's take, so this is something that we have seen previously, and I think we have also dealt with this in 614. But if you have not seen, if there exists a particle which in the real space, right, feels like this, which is everywhere in the real space. If this is psi of x, which is extending from 0 to infinity, right, then its Fourier space will be a single line, right? It's k, this is psi k, at k. It has a very specific k if it has a very specific k value or the momentum p is equal to h cross k, right? So if the particle is completely delocalized, if it goes in x from minus infinity to plus infinity, it lives everywhere here. You cannot tell with certainty where it exists from in this 3D space. It's everywhere. Then it will have one unique k vector. This is the plane wave, right? A plane wave can exist everywhere in the e power ikx mod of e power ikx is 1. Hence it will exist everywhere unique with equal probability. Then it has a single k value which is a perfect certainty of the momentum. So you will have complete uncertainty in the real space. In contrast, if you have a complete certainty of the position, let's say if I have the particle to be completely localized at x is equal to 0, right? Something very small and 0 everywhere. If this is my psi x, this tells me that the particle lies almost at the center all the time. Then its momentum goes like this, in the sense that in the Fourier component it will have a summation of all the plane waves with k's, with so many k's, right? And hence any measurement of momentum on this particular particle which is localized at one point will give you this huge spread which goes from minus infinity to plus infinity, right? So this is the trade-off that we know in the quantum picture, and this is called as the Fourier transform relation. Which is known classically before, but then when you impose a wave-like picture to a particle, the particle also experiences this kind of a behavior. If you localize a particle completely at one point, if you know for certain where the particle lies, then its momentum has infinite values. Every time you measure its momentum, it will give you a different value, and its variance will be from minus infinity to plus infinity, right? Now let us take a particle which is relatively free, right? Because we are talking about we get back to our previous problem here. Y is our classical particle having twice the velocity of the quantum particle, right? So let's go back to a free particle. We assume that the particle is not so free in the sense that it can go from minus infinity to plus infinity, but it has a very slow varying function which goes to infinity. Particle goes to 0 at x is equal to plus or minus infinity, right? So in this particular case, then the momentum is strongly peaked, right? It is allowed to go freely for a very long distance, but at infinity the particle anyway goes to 0. That's the assumption, right? The particle is allowed to go freely for a very long distances, but it goes to 0 at infinity. So in that particular case, you can assume that the momentum to be a very strongly peaked function about a value, let's say k naught. So this is the momentum. It will be a strongly peaked function, right? Actually it will not be like this. The actual psi k will have a sinc form, okay? We'll not go into this right now. Maybe we will see some homeworks regarding this. Even if you have a delta function, if you have an almost free space, then you will have a kind of a sinc function here, okay? So let's, okay, in that case I'm going to write psi of x comma t, that is this wave function, can be written as 1 by root 2 pi integral minus infinity to infinity psi k e power I kx minus omega t dk, and omega is just written as h bar k square by 2m. Okay, it's the previous expression just written here in a new form, okay? And we know this, that the psi k is strongly peaked Why? So this is the Fourier transform, right? So this Fourier one is going to be strongly peaked. When k is strongly peaked, we can actually write this omega in a, let's say, is strongly peaked at k naught. Okay, we are going to write omega naught in the Taylor series expansion. We write omega naught plus dou omega by dou k minus k naught. Because it is strongly peaked, you can expand this in this particular format. Then x comma time t equal to 0 will turn out to be 1 by root 2 pi integral minus infinity to infinity psi k naught plus s e power I k naught plus s x ds, right? Because at time t equal to 0, all the time components die. So this is the, at any time t, it can be written as psi of x comma t 1 by root 2 pi e power minus I minus omega naught t plus k naught omega naught dash t multiplied by an integral which goes from minus infinity to infinity psi of k naught plus s, as we got in the previous case, e power I k naught plus s into x minus omega naught dash t ds. So I have just replaced omega by this particular expression, right? And then I have substituted s equal to k minus k naught. So if you do this, you get this particular relation. This is pretty straightforward. And you can see this e power minus I term, whatever this term, will not contribute to psi x comma t square, right? Why? Because whenever you do psi cross psi, e power minus psi, e power plus psi will cancel, and then this term will not contribute. And only thing which contributes will be this term. And this term is basically the same function. So psi of x comma t square is basically psi of x minus omega naught dash t comma 0 square, right? If you replace x by x minus omega naught t, you will get back to the same equation. So this equation and this is the same if you replace x by x minus omega dash t. So what we are saying is at any time t, the wave function seems to be moved by this particular value omega dash naught t, which means that the velocity should be omega naught dash, which is dou omega by dou t. And omega we note to be defined as h cross k square by 2m, which will come out to be h cross k by m, and which is twice the velocity of what we got previously. We call this as, our previous quantum velocity is called as v phase, and which is twice the actual velocity, and this is same as v classical, right? So the velocity of a wave packet, if you have as a summation of several plane waves, then that velocity will be very similar to the velocity of the classical particle if you have a localized psi k, or if you have a particle which is relatively free. For a particle which is relatively free, then we get the psi group, v group. We call this as velocity of a group of waves, which, because we have it as a summation of waves, it's called a group. It's called a group velocity, which is twice the velocity of individual phases, which is the velocity of the plane waves that we have, and which is equal to the v classical. So now we have resolved the conflict by saying that if you have a particle which is a summation of several plane waves, then the velocity obtained from this quantum description matches with the velocity of the classical description, right? So we will finish this particular discussion with one last and an important topic is an harmonic oscillator. So an harmonic oscillator has its origin from classical physics. You must have seen a simple spring mass damping system, right? So let's say you have something which a mass m, it has a gravitational force, and if it moves by a distance x, the spring gives a restoring force equivalent or proportional to the moment of x, which is minus kx. K is called the spring constant. This is called the Hooke's law. So if you have a spring mass system, the total force on the mass is given by minus kx, which is the restoring force, and by the classical equation of motion, F is m d square x by dt square, which should be equal to kx, right? And the solution for this is d square x by dt square is minus k by m into x, and the solutions are x is equal to a sin omega t plus b cos omega t, and omega is just root k by m. Again, k is the spring constant and m is the mass of the spring. So this is something that we all know, we have seen this at many places. The energy of this particular oscillation, right? The potential energy will turn out to be half kx square. So what we mean is, as the displacement x goes from 0 to some higher value, the restoring force increases proportional to the square of x, and the gradient u, this is the potential, can be written as, the restoring force F is written as the gradient of the potential u. So the gradient gives you a linear x, which is the force, which is the minus kx. This is the restoring force on the spring, right? The Hooke's law spring force constant that we know of, right? So this is the normal classical description of a spring mass system, which you know well about. Now let's consider a quantum particle in this potential. This potential is harmonic in the sense it goes a square of the distance from this particular point, naught, right? So if I have a quantum particle in this, how do we describe a wave which tries to sit in this harmonic potential? A harmonic potential is one whose value goes as square of x, okay? There is nothing special about a harmonic potential. This is little different from the potential that we saw previously, right? These were square well potentials that we saw. Now we have a potential which increases with square of x, okay? So the Hamiltonian again is defined by p square by 2m and v of x, which we know now is by 2m plus half kx square, and k is omega square m, right? So which is half m omega square x square, which can now be written as 1 by 2m p hat square plus m omega x square, right? So this is the Hamiltonian. I'm going to define, so the Hamiltonian is an operator as we saw previously. Here you have everything to be operators. Now let me define another operator, okay? A dagger. We will see why I have to define it in this particular format, but for our purposes we don't have to go very deep into this. Let's assume another operator, okay, which comes with this constant root 2 h bar mw is just a constant, and it is defined as minus ip hat plus m omega x. I define another one, a, which is once again scaled by the same constant, ip hat plus m omega x. They are defined in such a way that if I multiply one by the other, a dagger a, okay, it will come out to be 1 by 2 h cross m omega p hat square minus I m w x hat p hat minus p hat x hat. Right? Now we know this is called as the commutator, and we know its value IH bar, right, from our previous descriptions. So if I substitute that, I get 1 by h cross omega into the Hamiltonian minus 1 by 2. And if I rearrange, the Hamiltonian can be simply written as h cross omega a dagger a plus 1 by 2. The same thing if I do, obviously remember these are operators, so a dagger a is not same as a dagger. The Hamiltonian can also be shown to be, can be written as a dagger minus 1 by 2. Both of them will give us the Hamiltonian. So I have just defined these two operators to make my Hamiltonian definition simpler, right? So my previous Hamiltonian definition was like this. I have now derived something which is a little different from the Hamiltonian with a and a dagger, but I have defined it in this particular format, which when acting on psi will give E psi. Psi will give E psi. Now the reason to define these operators a and a dagger is because if the Hamiltonian acts on a dagger psi, it can be shown that the energy gets increased by h cross omega. Right? So let me actually clarify this a little bit. A dagger is an operator, right? And let's say a dagger acts on psi and gives me a dagger psi, another operator, right? And if Hamiltonian acts on a dagger psi, it can be shown that the eigenvalue is E plus h cross omega times a dagger psi. A dagger psi is again an wave function, right? So we know that this is to be true, and I can show this to be true. So let's take a while just to show that this is true, right? So the Hamiltonian can be written as a dagger a plus half h cross omega. If this acts on a dagger psi, right? Now it can be, I can bring this inside, so I get h cross omega a dagger a dagger psi, right, plus h cross omega by 2 a dagger psi. I'm just expanding the brackets here, okay? So I'm going to just take this a dagger out, so h cross omega a dagger plus half, which can be written as a dagger h cross omega. So we have previously seen that a dagger minus half is same as h, right? So a dagger minus half plus 1 psi, which is a dagger h hat plus h cross omega acting on psi, which will be E, because H acting on psi will be E plus h cross omega acting on A dagger psi. So I have shown that H acting on A dagger psi. So this is an eigen equation, right? And A dagger psi is an eigenvector of the Hamiltonian, and the energy is E plus h cross omega, and E is the eigenvalue of just psi, right? So when A dagger acts on psi, it is just transformed into another vector whose eigenvalue is E plus h cross omega, right? So you just increase. The similar can be shown that if H acts on A psi, it will give you E minus h cross omega acting on A psi. So these are called as ladder operators because let's say if this is the ground state with E naught and it is called psi naught. A ground state is the lowest energy state of any system, okay? And there can be multiple steps here, right? So what these things do is if I take psi naught and act A dagger on top of psi naught, it moves a particle from the ground state to the first state, psi 1, and the gap and the energy is increased by h cross omega. If I again act with another psi, it moves a particle from here to here, same h cross omega, and makes it go to psi 2. If I operate a particle, if I operate, let's say I'm in psi n and operate A on psi n, it brings the particle down E minus h cross omega to psi n minus 1, right? It can keep coming down. If A dagger acts, it moves the particle up. If I operate A on psi, it moves the particle down. It cannot continue infinitely, right? So if A acts on psi naught, what do we get? I cannot have an energy E naught smaller than h cross omega. I mean h cross omega smaller than E naught because E naught is the ground state. I don't have any other states energy smaller than h cross omega. The only way this can happen is it goes to a zero state, right? So A psi naught has to be a zero state. So this is much easier to solve than the original Hamiltonian, and hence we have defined two operators, A dagger and A, such that you come to this reduced problem. So now I know the A operator, which is 1 by root 2 h cross m omega h bar dou by dou x. This is IP, right? Plus m omega x. Acting on psi naught should be 0 because psi naught is the ground state, and this is the definition of A, right? And this is dou by dou x of psi naught is equal to minus m omega by h cross psi naught, and the solutions are dou psi naught by psi naught is equal to minus m omega by h bar x dx. Integrate it on both sides. The solution will turn out to be psi naught is a e power minus m omega by 2h bar x square. So we have found the ground state of this entire Hamiltonian by just defining a new operator. Okay, this might all seem to be a little unsettling right now. We can repeat this again or revisit this so that we understand there are different ways to find the the solutions for a harmonic oscillator, I found this to be the easiest, but of course there can be other ways to do this as well. If this is the ground state, this has to be normalized to find A. So if you do psi naught star psi dx equal to 1, we can prove that A square will turn out to be root m omega by pi h bar, right? And the energy of the ground state, now we have to find what are the ground state energies, right? H hat acting on psi naught is h cross omega. A dagger A plus half acting on psi naught will actually give us half h cross omega psi naught, and half h cross omega is basically E naught. Therefore, the ground state energy of a harmonic oscillator is half h cross omega. Remember, the ground state energy, so basically the particle at rest, we saw that this is the potential, right? And this is the particle at x is equal to 0. So classically the particle at rest should have energy E naught to be 0. You expect the ground state energy to be thus. But the quantum derivation shows that the ground state energy is not 0 but half h cross omega. So the actual ground state energy of a quantum harmonic oscillator is not like this, but rather like this. This is h cross omega, right? So now that we have found the ground state, any other state psi n can be found by a dagger acting n times on psi naught. For example, psi 1, the first excited state, can be found a1 a dagger psi naught, and its energy E1 will be n plus half h cross omega. So the first excited state will have an energy 3 by 2 h cross omega. So I suppose we have gotten a little bit farther than what I expected to cover today, but we will stop here and we will revisit this harmonic oscillator once again. Thank you for your attention. Bye bye.